Hello everyone, and welcome to a college algebra video in which I will be covering exponential basics. So what we'll do here is I will start out with some vocabulary and notation. I will move on to exponent law review, just to bring those ideas back to the forefront. And I made this slide already and the rest of the video as well. So I'm going to be covering these next two topics in the other order here, evaluating exponential functions after we do exponent law review. Then I will move on to name that exponent. And finally, I will be solving exponential equations by similar base, which will heavily rely on being able to name that exponent. So again, these two topics will be switched. Let's get into it. All right, on this slide, I will have vocabulary and notation. So you can see here, I have the words exponential function. And remember, functions will have two variables. Generally, it will be a y and an x. Like you can see in this equation right here, y equals b to the x power, or more commonly, we will have f of x equals b to the x power. And I want to go over what these letters mean. B is what we would call the base, and the base will always have an exponent. And I may often refer to this as the power. The other thing is we call this an exponential function because the variable, guess what, is in the exponent. And that's exactly why it's an exponential function. I've said many times in my classes that in the story of algebra, we introduce the letter x, and then we do things to it like square it or cube it, and we put it places that generally make people upset, like in the denominator of a fraction, or in a square root, or in the exponent. And so this is the chapter in algebra where we move x from being in the term to being in the exponent. And that's how we create exponential functions. So very quickly, on a different note, an exponential equation with similar bases, I may also use the word like bases, has the same base on each side of the equation. And even better, I'm just going to say this, I'm not going to write it, there will only be one base on each side of the equation. So we can only have similar or like bases if there's only one base on either side of the equation. That'll make more sense in about 7 or 8 more slides. Very quickly on this slide, I want to go over some exponent law review. So really quickly over here with these three first, you can see that these are the only ones that are incomplete on the page. And these are the ones you are probably most familiar with. So if you have similar bases being multiplied, you can add your exponents together and combine them into one base. So here I have base b to the m plus p power. And if you're dividing, like here, you can either write it as b to the m minus p, top minus bottom, or you can even write it like this, 1 over base b to the p minus m. And this expression is a little bit different because the m comes first, and down here the p comes first. And these are all exactly the same. Let's see. if you have b to the 0 power, that will be 1. And later on in this unit, you'll see that the base for any exponential function is going to be bigger than 0. But more generally, any number to the 0 power is 1 as long as it's not 0. So we can say non-zero bases to the 0 power is 1. Let's see. So these over here, I think these are where most students really get upset is with the negative exponents. And in math, and I'm telling you, this is all the way through master's level mathematics, negative exponents are considered, big air quotes, ugly. We don't like them. We like exponents to be positive. So to get rid of a negative in an exponent, you can swap the base and the exponent to the opposite side of a fraction. If you think of this as being over 1, you can swap it to the other side of the fraction and make the exponent positive. That's how you make an exponent positive. You just take the base and the exponent and put it in the other side of the fraction. So rule 1 and rule 2 here are just how to deal with negative exponents. Rule 3 here is really 2 in 1. Here we have an entire fraction with unlike bases or different bases in the numerator and denominator to the negative power. And to get rid of this negative power, you would take the top and move it to the bottom, and you would take the bottom and move it to the top, just like you would if it was here. For this, we could also say we could take the reciprocal of this fraction and we could make the exponent positive. But even on even better, on top of that, we can distribute this exponent to each base in the fraction, just like we can distribute an exponent to each base, even if they're being multiplied. So that was just a quick exponent law review. You will see a lot of these exponent laws be used over the next few slides and the next few sections. So even if you don't memorize all of these right now, you will have a lot of examples using these in the very near future. Before we get into function evaluation, on the next slide, I want to look at one more equivalence that you will want to get used to as we start working with exponents. And it's everybody's favorite type of exponent ever. This is what we would call a rational exponent. A rational exponent. And to most people, a rational exponent doesn't make any sense. Like, let me just give you a quick example here. We could say 9 to the 1/3, the 1/2 power. That doesn't make any sense. What does 1/2 power even mean? I didn't even know you could have a fraction up there. Yeah, well, anywhere you can stick a variable, you can stick a fraction. So here is how you can interpret this so that you can make some sense of it. And even worse is you get choice. So if you have a rational exponent, you get to choose whether or not you want to write it like this, with the t on the inside as the exponent, or the t on the outside as the exponent. So you can see in either case, if you have a fraction, that's going to turn into some kind of root. All right, so again, we have a root here. And again, the exponent, the top, will become the exponent, the bottom will become the root. So you can think of this as the bth root of a to the t power, or you can think of this as the bth root of a to the t power. Anyway, looking at this example down here, 9 to the 1/2 power, this would be the root and this would be the exponent. So it would look something like this. The second root of 9 to the first power. Well, the second root of 9 is more commonly known as the square root of 9. And the square root of 9 is something that makes a heck of a lot more sense to most people. So a square root of 9 is 3. 3 to the first power is just 3. And this can be done all sorts of different ways. Like I could put here something like this. Let's say 64 to the 4/3 power. The denominator of the exponent will always be the root. The numerator will be the exponent. So this is the third root of 64 raised to the 4th power. Now you can use technology, computer calculator, something to figure out that the third root of 64, or the cube root of 64, is in fact 4. And then you can raise 4 to the 4th power and get 256. But again, in this form, it doesn't make any sense. Most people understand roots better than they understand rational exponents. And I wanted to point this out. It will show up when we start doing function evaluations in 3, 2, 1. Function evaluations. Here we have a function if f of x is equal to 3 to the x plus 2 power. Yeah, we can add numbers in the exponent too. Then we should be able to find f of 2, f of negative 2, and f of negative 5. So here I have these all set up, and it's just like every other function we've done. If you substitute 2 in for x in the function notation, you substitute 2 in for x into the exponent. So it'll look something like this. This would be 3 to the 2 plus 2 power, which would be 3 to the 2 plus 2 is 4th power, and 3 to the 4th is 81. Similarly, we can substitute negative 2 in for x in this function. So negative 2 plus 2, which would be 3 to the 0 power, which would be just 1. And here, the last one, f of negative 5, it's as simple as substituting, you guessed it, negative 5 in for x plus 2, which would be 3 to the negative 3 power, and negative exponents are no good. So what we need to do is we need to push this to the other side of the fraction, and then we can make the exponent positive. So 3 to the 3rd power is 27, but it would stay in the denominator because that's where the 3 to the 3rd power was. So here's our answer for that. Let's take a look at one more example. Okay, here's one more example for function evaluation. This time, if we have two functions, g of x equals 1 over 25 to the x power, and h of x equals e to the x power. Now, I'm going to make it formal here that bases must be bigger than 0 and not equal to 1. So when I say bases must be bigger than 0, that just means any positive number. Literally any positive number, even if it's a fraction. And then we can also include numbers like e. E is approximately 2.71. We often call it Euler's constant. Yes, if you are in the Pearland, Texas area, Euler, that's how you say it, Euler's constant. And it's equal to 2.71 every single time. It's kind of like pi, but just a different number. So we can substitute these numbers in. So if g of x equals 1 over 25, all of it raised to the x power, we can find out what g of 2 is simply by substituting 2 in for x. So let's do that. G of 2 equals 1 over 25. Guess what? We substitute 2 in for x. And then we get to use this, this property, right, that I went over a few slides ago that said if you have a fraction being raised to an exponent, you can take that exponent and raise the base in the top and the base in the bottom to that exponent. So this would be 1 squared over 25 squared, which is 1 over 625. And no, we do not want decimals here because you guys can figure out 25 squared, and since it was in the bottom, 625 will stay in the bottom. Let's take a look at g to the negative 1/2 power. Okay, here comes your half. I said this was going to show up here. All right, g to the negative 1/2 means we can write down 1 over 25 to the negative 1/2 power. And there's a lot going on with this exponent. The first thing I don't like here, and the first thing you want to try to take care of anytime you see it, is a negative exponent. So the negative exponent says we can basically swap this entire fraction around. It's a reciprocal. So if I reciprocate this fraction, that is flip it, I will get 25 over 1, which is just 25. But that's nice because we get to get rid of the negative now. 25 to the 1/2 power doesn't make any sense until we write it in a radical form. Remember, the denominator goes in the root and the numerator turns into the exponent outside the root. And you might be wondering, well, hey, you did not write the 2 in the root. Normally, we do not write the 2 in the square root, but if you put it there, I don't think any teacher or professor would be too upset with you the first few times you do it, but just make sure you don't make a habit of it, because that 2, we understand. Everybody who teaches math and loves math understands that that 2 is in fact there. So we don't write it most of the time. In fact, we don't write it ever. So the square root of 25 is 5. 5 to the first power is 5. Awesome. All right, next, h of 0. That would be h of x over here in this side. That would be e to the 0 power, which, well, luckily for us, that's just 1. And lastly, we can find h of negative 7. And that is going to look like this, e to the negative 7 power. But again, with the negative, we can't have the negative. So just like I did in the last slide, we will push that into the opposite side of the fraction, which will look like this, 1 over e to the 7th. And that's it. This is what we would call an exact answer. And it saves you from having to think about what e to the 7th power is or possibly miscalculating it in your calculator. So anytime you're dealing with e, you just want to leave it the base e with whatever power it is. And now it's time for everyone's favorite game show, Name That Exponent. Here's your host, Professor Greg. Thank you, everybody. Thank you. We are now going to play a relatively easy game here. I'm going to write an equation up on the screen. One side will have a base with a variable exponent, and I just want you to tell me what exponent you need to equal the left side. Let's take a look at our first example here. All right, out of the gate, we have 3 to the x power equals 9. And all I want you to do right now is stop, take a few seconds, ask yourself, what would x have to equal here so that I can raise 3 to this power to give me 9? And if you out there are saying x would have to be equal to 2, great job. If you don't understand what's going on yet, hang in there. There will be plenty more examples. So here, let's take a look at 7 to the x power equals 343. You take a look at this, maybe off in a calculator you multiply a few 7s together. Just keep track of how many 7s are actually being multiplied. 7 times 7 is 49, that's 2 of them, times a third 7, that's 343. Looks like we need 3 7s to be multiplied to give you 343. Ooh, I've got a good one. How about this? 2 to what power? 2 to the x power gives you 1 over 32. We're just trying to think, what exponent do we need to make this happen? Well, I'll tell you one thing, it can't be a positive number because 2 is in the top half of the fraction over here, and our number is in the bottom half of the fraction over here. If we switch sides of the fractions, oh boy, I know already that has to be x equals negative. That has to be a negative number. The rest of the answer then, the actual number part, is what power of 2 do you need to get 32? Well, think about it. 2 times 2 is 4, times a third 2 is 8, times a fourth 2 is 16, times a fifth 2 is, there we go, we need 5 of them. 2 to the 5th power. That 5th 2 would multiply to give us 32. All right, let's take a look at another one. We can take a look at pi. Oh yeah, pi is coming in. Here it is. Pi to what power would give you 1? I promise you there's only one number here that will work. It's exactly what x should be equal to in this box right here. We had this rule a few slides ago. It was rule number 7. It said the base to this power is always going to be equal to 1. Let's see. Pause for effect. Let the suspense build. It's 0. Remember that? Any non-zero base to the 0 power will equal 1. Sweet. So now that you've seen that, how about this? 1,239,4.6198 to the x power equals 1. Can I trick you here? Are you going to know what this is? Can I trick you? What exponent do we need here for this crazy made-up number that I just did right now? Huh, alright, well, I guess it's just 0 again. I don't think I can fool you guys. I've got one more, and I'm going to call this my challenge problem for this slide. Let's see if you guys can figure out this. 64 to the x power equals 8. Ooh, yeah, I'm going to get even the smartest of you out there for this one. Alright, let's think about this. We can't use multiplication or division. We have to use an exponent. But the exponent we're looking for normally doesn't make very much sense. So if I thought about it, what can I write around or in addition to this 64 to have it turn into 8? It's going to have to be a square root. How do you represent a square root as an exponent? Well, we know that there's a 2 in the root here, and that the exponent on 64 is a 1. It's 64 to the first power. So our exponent would be 1/2. So please commit this one to memory. Half power means square root. Square root means half power. Half power means square root. Square root means half power. I guarantee if you go around your room or around your house, especially in 2020 when we are all social distancing and staying home, and your parents or your kids will just think that you're either crazy or super smart. Or both, I guess, would be fine. I'm hoping they think you're super smart. If you walk around and say half power means square root means half power. Let me know how that works for you. Lastly for this video, solving exponential equations by similar/like bases. And I say we just jump right into an example, and I will get the process out to you through this first example. So in order to do this, I've always found it easier to start with a slightly more difficult example than what you saw on the last slide. So we will look at something like this. So for this example, we can see that we have a base on the left and a base on the right. And what we want to do is we always want to try to make the bases the same. So I either want to make this into a base 27 or this into a base 3. Now here's a pro tip. Choose the smaller base. So when I was saying you want to change 3 to 27, no. You want to change the 27 to base 3, yes. That makes it so much simpler. So we always want to choose the smaller base. So what happens is we will have 3 to the 2x plus 1 power equals 3 to, well, what power of 3 do we need? You can see why we were playing the name that exponent game. So right here, I'm trying to figure out what power of 3 do I need to give me a 27. In fact, we need a power 3. So we are rewriting the bigger base into the smaller base and giving it some exponent. Why is that helpful? So once you have similar bases on both sides, you are then mathematically allowed to set each exponent equal to each other. So it's almost like we get to get rid of these bases and set the exponents equal to each other, leaving us with this new equation, 2x plus 1 equals 3, and this is so much easier to solve. This looks a lot easier to solve than staring at this problem for 25 minutes asking what the heck is going on. So you can subtract 1 from both sides down here in the purple equation to get 2x equals 2, and then you can divide both sides by 2 and get x equals 1. That's simple. These steps. So getting similar bases, we always want to move a larger base to a smaller base. And then once we have similar bases on each side, we can set the exponents equal to each other and solve. All right, let's take a look at the next example. So here are a couple more examples. You can see in the first equation, the only direction that you're going to have here is solve, or it might say solve the following exponential equation. But you will know it's exponential because the variable is in the exponent. So here we have a base 7 on the left and a base 49 on the right. Well, I want to turn this into a base 7. I want to make this base smaller. So for that, I just have to ask, what power of 7 gives me 49? It's 2. So we can then more or less just get rid of these 7's and set up this new equation here, negative x equals 2. And if you want to solve for x, you can divide both sides by negative 1, which leaves you with an x equals negative 2. Sweet. Ooh, this one's a little interesting over here. Solve 5 to the x over 2 plus 1 power equals 1 over 5. Now here is something you don't see every day. We have an exponential equation with the same, oh, this isn't the same base. Oh man, this is 1/5. This whole fraction is the base. Whereas this side, it's 5. I don't want to turn a 5 into a 1/5, even though 1/5 is smaller than 5. Maybe we should get rid of the fraction. Maybe we should turn any fractions we see into a whole number base. That sounds like a good idea. All right, let me start writing. The left-hand side here is pretty simple. This is still going to stay 5 to the x over 2 plus 1 power equals 5 to some power. Yeah, that'll look better than trying to have more fractions. We already have one in this exponent. We can at least get rid of this one. What exponent will I need for 5 to move it to the opposite side of a fraction? Well, it's got to be negative. Has to be negative. That's the only way we can flip-flop sides on a fraction. And what number do we need? 5 to what power gives me 5? Well, it's just going to be 1. 5 to the first power is 5. Cool. We now have a like base on both sides of the equation. So again, what we can do is we can more or less, this is kind of mathematically what's happening. We get to cancel the bases and set up a new equation. We have x over 2 plus 1 equals -1. Now, in the way I've taught this, I want to get rid of my fractions first. So I'm going to find my LCD here was 2. So I will multiply everything by 2. There we go. Then that'll cancel with this 2 here, leaving me with x plus 2 equals -2. And then I can subtract 2 from both sides to get x equals -4. I've got two more examples for you. One of I think is going to be easier, and then the other one I think I'm going to call my challenge exercise. And I'm wondering if you guys out there can correlate that to anything I've already said in this video before. Let's take a look. Okay, last couple examples. Let's crank this out. I see 6 being raised to a 3x power here and 216 being raised to this power here. This is clearly the smaller base, 6, so I want to rewrite 216 as a base of 6. What makes this different from any other one that we've seen so far is that both bases have their own exponent. There's an exponent for each base here. So we have to keep that in mind. The left-hand side here will not change. This will just be 6 to the 3x power, no problem. But we have to figure out then, right in this little box, right here, what power of 6 would give me 216? It would be 3. But then we still have this exponent, 5x minus 4. And as I am doing this exercise, I'm realizing that I forgot an exponent law. So let me write that right down here. I think we were on number 8. If you have a base that is being raised to a power, and it will be raised to yet another power, you will multiply those powers together. So, with that being said, we have to multiply these exponents together now. And when you do that, you have to think that there is a set of parentheses around this 5x minus 4, and that this 3 will get distributed to both. Remember, if you're going to multiply a single term by a two-term expression, we still need to have two terms at the end. So we will have 3 times 5x is 15x, and we will have 3 times negative 4 is negative 12, resulting in an equation that looks like this. 15x minus 12. There it is. Now we have similar bases. Let's go ahead and set those exponents equal to each other and solve. So I've got 3x equals 15x minus 12. I can subtract. I'm going to subtract 15 x's from both sides. To get me negative 12x equals negative 12, and then I will divide by negative 12 to get x equals 1. All right, challenge example time. Here we go. I have, oh my goodness, I have 1 over 9, and you've seen something like this before. I want to get that out of the fraction form as quickly as I can. I know I can raise 9 to the negative 1 power. That's fine. And on the left side, I still have an 81 to the x power. Well, now would you look at that? This is the smaller base. This is the smaller base. So I need to turn this 81 into a smaller base. So just right here in this little box, I want to rewrite that as 9 to some power. But even better, we still have it raised to the x power. So I can rewrite 81 as 9 squared. There we go. So what do I do now? I have an exponent, 9 with an exponent being raised to another exponent. I can multiply those exponents together. So I will have 9 to the 2x equaling 9 to the negative 1. So now I can do this. I can reduce you guys away, set you equal to each other. 2x equals negative 1, which means x equals negative 1/2. One last time, this 1/2, look at that. That would be an exponent, or a power, we could say. Half exponent equals square root. Square root equals half exponent. So look at that. If you take the square root of 81, you would get 9. But this 9 is in the bottom of a fraction. This 81 is not. That's where the negative comes into play. The negative would shove that 9 right down to the bottom. Now on to everybody's favorite topic, money. Compound interest. So this is the money portion of this course. You can see here there will be 2 formulas, and they will be given on the exam. And you can see that there are these 2 formulas here, and also there are many more formulas that help describe the mathematics behind the finances that happen, but for this course we will just concentrate on these 2. So here on the left we have what we call the compounded nthly. All right, compounded nthly, which is kind of a weird way to say it, nthly. And we'll talk more about that in just a minute. And on the right-hand side, we have compounded continuously. And the difference between these two is nthly and continuously. You can see this word compounded. That just means how often would you make or pay interest. So if you're doing it nthly, that could be monthly or weekly or yearly, things like this. But if it is compounded continuously, then we don't have a reason to use the n, which is why you don't see an n here, to tell us how often we're getting interest. You are continuously getting interest. So what are the differences between these here? So A, you can see A is common in both equations. So there's A, there's A. That is what we call the accumulated amount, aka the ending amount. P, which you can see is in both equations, P is what we call the principal or the beginning amount. R, you can see, is in both. It's in the top of this fraction, and here it's in the exponent. That is the rate, and we need it to be a decimal. T, you can see, are in both equations. That is time in years, and that just leaves n, and n is only in this formula here. As I mentioned, the differences for n here can be pretty widely varying. We can have n be equal to the number 1, we can have n be equal to the number 2, or 4, or 12, or what is that, 52, or even 365. All of these numbers represent how many times you would be getting interest in 1 year. So we just have to name these accordingly. If something only happens once a year, we would say that it happens annually or yearly. If something happens twice a year, we could say that to be semi-annual. 4 times a year would be quarterly. There are 4 quarters in a year. Or I guess we could call this number 2 semi-annually or semi-annual. If something happens 12 times per year at equally spaced intervals, we could assume that that would be called monthly. Here we have weekly, and the last one would be daily. Now, that being said, the most common of all of these are going to be annually, because that can happen in the real world. We can have quarterly and monthly. Those are probably the most common ones you'll see in the real world and in exercises. The only other type of compounding we can have is over here. We talked about this already. Continuously compounded. One last thing before I go to the next slide, and that is just a very quick reminder. You'll notice this letter is not listed anywhere down here. We have N, A, P, R, T, but we don't have E listed because E is a constant. Again, it is very much like pi. It is 2.71 power. 2.71 approximately. All right, let's take a look at examples. On this slide, we have a couple examples here, the first of which reads, at age 25, you invest $30,000 in an account yielding 9% compounded monthly. How much will you have when you retire at 65? That's age 65. So what you want to do, the easiest way to figure out all this stuff here is to write down A, P, R, T, and then N. And I know we will need N because it tells us compounded monthly. That's how I know we will need an N. And in fact, we can say that n here will be 12. All right, let's see. Let's see, we invest an amount. So the amount that you begin with, the amount that you invest will always be your principal. So the principal here would be 30,000. We can see the interest rate is here, yielding 9%. That would be your interest rate, but as a decimal would be 0.09. So if you have 9% and you're trying to find the decimal, you have to move the decimal point 2 to the left. That's where the 0.09 comes from. Next, the last thing we need is time. In a lot of the examples you'll look at, it'll say, oh, for 25 years, oh, for 7 years, oh, for however many years. But sometimes it can be hidden like this. We know for sure we've got this ending age of 65 and we have this beginning age of 25. And we have to subtract these two, and it's not a very difficult calculation. You can see that the difference between them is 40 years. What we're trying to figure out here is our accumulated amount. How much will you have at the end of this 40-year period? So what you can do from there is write down the formula. A equals P times 1 plus R over N to the NT power. You can substitute all of the values in like this. You can do a couple calculations here to make the calculation on the calculator easier. And that will be, you want to divide the rate by the n, by the number of compoundings per year. And you want to multiply these numbers in the exponent, which will give you something that looks like this. And from here, you can just type this into most calculators. It is suggested that you figure this portion out first. You can type in 1.0075 raised to the 480 power. You can use this button to raise any number to a higher power. And very quickly, this 1.0075 comes from just taking the decimal you get from dividing this fraction and putting it after a 1 with a decimal here. So if you figure this portion out first and then multiply it by 30,000, $1,083,297.06, which is just a lot of money to think about. So that's pretty sweet. The next scenario is asking, how about we have the same scenario if it was continuously compounded instead of monthly? And this word right here is your clue to be using this formula. A equals P e to the RT power. This is what it means to be continuously compounded, this formula right here. Now you would still want to go through and write down everything that you can. We have an A, we have a P, we have an R, we have a T. It just so happens that all of these items are going to be the same as the one above 0.09. The time is 40. And when you substitute these numbers in, e to the 0.09 times 40, again, you want to make sure you figure out what this exponent is. So you have A equals 30,000, e to the 3.6 power. And if you want to figure this part out on a calculator, you need to look for a button that says E with a little caret after it. or it might look like E with a little box up here. And you may have to hit a second or a shift button to access that. But then once you get that, then you can multiply by 30,000. And then after you do all that, you'll see that you get 1,097,947.03. So while you don't make much more than you did if it were monthly, compounded monthly, you still make more. And that is one of the things that is awesome about compounding. If you keep the same principal, the same rate, the same time, and you increase the number of compoundings, you increase the number of the amount of money you make. If you decrease the number of compoundings, you decrease the amount of money you make at the end, the accumulated amount. It's a very nice system. So if you go to a bank and they offer you yearly interest payments, and you go to a second bank and they offer you the same interest rate, and they say, hey, we'll give you interest monthly instead of yearly, you want to pick the monthly rate. This is the same reason credit card companies compound your interest daily. They only charge it to you one time per month, but credit card companies compound your interest daily because they know they can make more interest, not much more, but more interest if they compound it daily instead of monthly. That's the lesson for exponential equations and applications. Stay tuned for a quick message from my awesome little kiddo. Oh, say hi.
Hi. That's my name. I'm Greg's daughter.
Yeah, I talk about you sometimes.
He talks about me sometimes, and yes, so thank you.
You want to be famous on YouTube someday?
Yeah.
Yeah?
Yeah.
What else do you want to do? What do you want to do when you grow up?
Be a singer.
A singer. What happened to be? You don't want to be a dancer? I thought you wanted to be a dancer.
Singer and dancer.
Singer and a dancer. So you want to be like Taylor Swift? Or like Sia?
I want to be like Dua Lipa.
Dua Lipa. Yeah, that's it. You want to sing and dance. That's cool. Are you missing your school friends right now? Yeah.
I kind of wish we could go to the park.
Yeah. It stinks being a 7-year-old right now, doesn't it? What do you get to do instead of go to the park? What are we going to do tomorrow?
We are going to do silly string and volleyball.
But not at the same time.
Yes, not at the same time. That would be too confusing. We'll do it at the same time.
Yeah. All right. Tell everyone bye.
Bye.
So thanks for stopping by.
Thanks for stopping by.